So this is a problem for a two-stage CMOS amplifier. And we're given these parameters in this table right here. VT for both PMOS and NMOS is 0.5 volts and VA is 10. We want to fill in the rest of the table. So for a two-stage CMOS amplifier, we know that Q1 and Q2 have to be matched. So Q1 and Q2 are located here. So if the width and length of 1 is 33, we need the width and length of 2 to also be 33. We're also given that the current, reference current, is 2 milli, which means that 2 milli will also go through here and here, because Q5, 8, and 7, Q5, 8, and 7 all have the same width and lengths. So as this comes down through the differential amplifier, it's going to split equally, so we have 1 milliamp for each of these. So 1, 2, 3, and 4 will each have 1 milliamp. And 5, 6, 7, and 8 will have 2 milliamps. From the current, we can find the VOV for each of these transistors. For 1 milliamp, for a PMOS, at 1 milliamp, which will be 1 and 2, we have 60 micro amp per volt squared, and the width and length is 33, and VOV squared. And now this is just one unknown, so VOV can be solved. And that gives a VOV of 1. So 1 and 2 are 1. For the NMOS at 1 milli, that they're 180 micro with a width and length of 11 and VOV squared. So VOV can again be solved. So that will be the square root of 2 milli, 180 micro, 11, and that gives also a value of 1 volt. For the 2 milli, for PMOS, again, that will be 5, 7, and 8, so 60, and they have 66. And that gives a VOV, solving that, of 1 volt also. And the NMOS, which will be the Q6 at 2 milli, you get 180 and 10, and that gives a VOV of 1.5 volts. So this is the only different one for all of those. So for VGS, we have that VOV is equal to VGS minus VT, and VT is 0.5, so we can use each of those. VOV is equal to VGS minus VT. And so we can solve this for the VGS is VOV plus VT. So we end up getting 1.5, 1.5, 1.5. And then we'll get 2 here. Okay, so for GM, we know that GM is equal to 2ID over VOV. So we can use that for each of these. So we have 1 milli and 1, so we get 2 milli for those that have 1 milli ID and 1 volt for VOV. So that gives us 2. These are already milliamps per volt, so I'm going to write 2, 2, 2. And then for the 2 milli, over 1, we get 4 milli. So that will be this one, and this one, and then we get the GM is 2 milli ID, and then the VOV in this case is 1.5. So we get 2.7 milli for that GM. For RO, RO is equal to a VA over ID. So we have VA was given as 10. So we have 10 over 1 milli. We get 10K. And then we also have 10 over 2 milli, so we get 5K. So this will be 10K, 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 and then 5K, 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 and 5K. So now we filled in the entire table. We want, another question is that we want to know if we put on the output of this a circuit that requires a DC bias. So the output needs a DC bias supplied to it of 2.3 volts. Is this possible? So we have to first think, well, what is going to determine that? One is the limitations of the CMOS op-amp. So 2.3 volts would be the high. So we need to check the high maximum possibility for VO. So VO max is going to be determined by Q7. And so that's going to be determined by the transition of this from triode to saturation, which is the condition of VDS equal to VGS minus VT. So this quantity here is VOV for 7. VDS is going to be your V out max minus your VDD. And this is actually a PMOS, so you're going to do it backwards, so it's VSD. So we have that VS is VDD minus V out max. So V out max will be VDD minus VOV 7. So we get 3 in this case, and the VOV for 7 is 1. So 2 volts is the maximum we can have, which means that no, this is not possible. The max out that we could get is only 2 volts, so it would not be able to supply that bias voltage. Another thing we want to find in this is the overall gain. So the overall gain is the gain of the first stage, A1, and the gain of the second stage. So this is your first stage, and this is your second stage. So the gain of the first stage is a differential op-amp. So that is determined by the GM2 of this transistor. So RO2 in parallel with RO4 is the output resistance. So in this case, GM2 is 2 milli. And RO2 and RO4 are the same, and they're 10K. So 10K in parallel with 10K will be 5K. So we get a minus 10 volt per volt. The second stage is a common emitter or common source amplifier. So you get a minus GM6 is the transistor that's going to determine the gain. And then it's the output resistance RO6 in parallel with RO7. RO6 and RO7 are the same. So they have 5K for RO, so we'll just take a half of that. This is 2.7 milli, and then a half of 5K is 2.5K. So we get that the gain for both of these is going to be the multiplication of A1 and A2. So we have a minus 10 volts, minus 2.7 milli, and a 2.5 K. And that gives an overall gain of approximately 67 volt per volt. We also want to know the frequency response information. So for the frequency response, we need to know the capacitance that is seen at the output, C2. So given that C2 is equal to 1 picofarad, we want to find FP2. So FP2 is GM6, the small GM6, over 2 pi C2. So in this case, 2.7 milli over 2 pi 1 pico gives a value of 429.7 megahertz. We want to also design this to give us a compensation capacitor value so that F of t is going to equal 300 megahertz. So F of t and the compensation capacitor are related by Cc being the small GM2 all over 2 pi F of t. So GM2 was 2 milli and 300 megahertz for F of t, and that gives a value of approximately 1.1 picofarad for the compensation capacitor. So knowing the compensation capacitor value, we can find the first pole, FP1, and F of z. So this was FP2, and this is your compensation capacitor. So FP1 is 1 over 2 pi R1 Cc big GM2 and R2. And recall from the model we did, R1 is R02 in parallel with R04. GM2 is the big GM2 of the second stage, which is GM6. And this is the output resistance R2 of the second stage, which is R06 in parallel with R07. So plugging these values in, R2 and in parallel with R04 is 5K, 1.1 pico for Cc. This is 2.7 milli for GM6, and then this is 2.5K. This gives a value of 5.8 megahertz. So this is FP1. FZ, which is your 0, remember it's a positive 0 instead of a negative 0. And FZ is equal to a big GM2 over 2 pi Cc. So this is GM6 over 2 pi. This is 1.1 pico. And GM6 is 2.7 milli. And that gives a value for FC of 289 megahertz. So here we see that, this should be a direct indication that there's something wrong. F of t we had designed for was 300 megahertz, and this F of z is lower than F of t, which is going to make